In this video, I want to talk about the realignment process, and in particular, we're going to talk about estimating the parameters of head motion so that we can start the realignment process. Realignment is going to occur in two phases. First, we have to estimate how much head movement is in the data, and then second, we need to correct for that head movement, by which I simply mean that we're going to reslice the data in a way to try to account for some of the effects. It will not account for all of them, and that's something I'll talk about in some length. Okay, so the fundamental problem that we always have to deal with is that when you put somebody in a scanner, their head moves. And you've probably had this experience just taking photos with people. If you take a photo of someone who's moving, it tends to be a blurry image. It's not a good photo. It's exactly the same situation in the scanner. The more somebody moves, the more difficult it is to get good quality data out of them. And people move because they're alive, essentially. They're not trying to be difficult. They're not doing something to be annoying. And it turns out that historically people have tried to do fairly dramatic things to get them not to move. One of which is to include bite bars. So that is to take like a dental mold of the individual subject, create with a dental concrete, such that you're positioned, when you're in the scanner, you're positioned with your teeth exactly in the right spot. And if you move them, it's incredibly stressful on your mouth. You can break your teeth. I mean, you really don't want to move under those circumstances. On the other hand, it's an incredibly stressful thing. It's not comfortable, and it really causes participants to focus a lot on not moving and not breaking their teeth, rather than, for instance, paying attention to your experimental paradigm. There were these thermoplastic masks that were used at one point where you end up with this person who sort of essentially got what amounts to something like a heavy saran wrap around their face with eyes, nose, and mouth holes so that they can see and breathe. And then that got shrink wrapped on your head in order to try to keep you still. And this has exactly the same effect. It does, but it's incredibly uncomfortable and people don't like it at all, and it makes people more anxious, and as a result you lose data quality because people aren't paying attention to the paradigm the way they would be if they were comfortable and relaxed. So what we normally do, and what most labs at this point do, is use much softer kind of approaches. Typically what we do is we spend some time reminding people that we'd like them to lie as still as possible. And then we put sort of soft cushions next to their head that don't stop them from moving at all. They could certainly move if they want to, but it does remind them because they can feel it if they move. And that's not a much better approach, because even so, some people will move, but you're not sort of forcing them into a position where they can't move and therefore making them extremely uncomfortable, perhaps exacerbating feelings of claustrophobia, etc. All you're doing is sort of relying on the fact that they volunteered to be a part of this experiment. They're there volitionally, and they're trying to help as best they can. So you're taking that on board and giving them credit for it by just giving them simple reminders at a real tactile level from these soft pillows that their head won't move. It's harder for things like scanning children. So if you're scanning kids that are like under 10 or 11, they forget this. I mean, as much as they'd like to help, they tend to be super energetic. They don't like lying still, and it's a different situation in those circumstances. But for adults who are cooperative participants, this is an approach that works really well. The problem with head movement is that when we look at the data, a particular part of the brain isn't in the same spot of the image, right? Because literally the head's moved. And that's going to be a real problem when we do our statistical analyses. So what we need to do is divide the image up into what we call three-dimensional voxels, which are volume elements. It's sort of similar to the idea of a pixel in your TV screen or on your computer, which is a picture element, but that's only in 2D. So in 3D, we refer to these elements as voxels. And the content of a given voxel needs to be the same piece of tissue over the time series in order to do an analysis that's meaningful. Otherwise, you're analyzing something that's not the same source of not the same source of neural tissue that generates the information. So to deal with this, what we need to do is realign the data that we collect, estimate the amount of motion that's there, and then simply interpolate it into a common stable reference. And that's what realignment is going to offer us. So this is another short video. In this case, what we have is an axial slice here, And what I'm going to ask you to do is pay attention to the voxel under the crosshairs, right? Because you can see that it's definitely changing. I mean, this is an example of really bad head movement in this individual. But if we just go back and look at this again, this place on the screen is clearly part of the ventricles at the beginning here. It's right on the edge, so it might be a little bit of ventricle, a little bit of gray matter surrounding it. And as it moves, you can see this is definitely ventricles at this point. We've even changed position. We're down into gray matter now. This is somebody who's really jumpy in the scanner. And this is the problem. If we want to analyze the data from this voxel, it's not the same neural generator for the whole process. So this is just a sort of illustration where what I'm doing is this is the same subject plotted over time, and it's that same voxel. And all I've done is plot the intensity of that voxel. And you can see it starts out sort of in an intermediate state, immediately goes into the cerebral spinal fluid of the ventricles, where you get a really bright signal in T2 star, bold signal. And then there's a drop-off that's rather dramatic around volume 50, where it moves into gray matter, and you start to see variation there. And this is the problem. And I don't need to know anything at all about the nature of the paradigm that this person was performing to know that this is a problem. The data are problematic because of this rather excessive head motion. So the way we deal with that is what we do is we begin by trying to estimate how much head motion is there and what was the nature of that head motion. And the first step here is to assume that the brain that we're looking at is a rigid volume. That is to say that the shape of the brain isn't changing over the scan. And for, common sense reasons, that seems incredibly sensible. It's the same person's head. It's really not changing every 3 seconds. All that's changing is the position of the head. And as a result, this rigid body transformation suggests that what we can do is we can move this brain in 6 directions, what are known as 6 degrees of freedom. 3 of them are rotations. So that is to say, we're going to create a plane where we're going to refer to left-right as the X plane, front-back as the Y plane, and up-down as the Z plane. So you have rotations on X, which are basically nodding, rotations in Y, which are pitch and yaw, and rotations in Z, which are sort of normal head rotations. Right, so those are the 3 types of rotations that you can do that don't change the shape of the brain. All they do is change its position. Similarly, you can have translations in X, Y, and Z. So that is to say movement from like left, right. I can't do it. It's sort of more of a Bollywood thing to be able to do that right. But you can move your head sideways. You can move it front, back. You can move it up, down. Those are the 6 degrees of freedoms that we're going to talk about. 3 rotations, 3 translations. And this image is showing translations on the bottom and a rotation at the top, where you can see that the shape doesn't change. All it changes is its position. And there are fairly simple ways to estimate those movements. But what you have to do in the first place is decide what your frame of reference is. What's your starting point? And your starting point varies a little bit depending on which software package you're using. So in SPM, which is the software that we're going to be using, it just assumes that the first volume in the data is the starting point. And that's a completely sensible thing to do, right? Because start at the beginning. Now, when I say first, I do mean first after you've deleted all your dummy scans. We're going to take them out first thing first. Then what you're left with is the data that you're interested in terms of your analysis. So the first of those volumes is your 0 point and your reference point. And all you're going to do is estimate, for instance, the pitch, roll, and yaw, the 3 rotations in X, Y, and Z, over the rest of the time series. So, and you can see that in this top plot. Pitch is shown in blue, roll is green, and yaw is red. And you can see that over the 88 volumes that were in this particular time series, the person moved however they moved, right? One of the things that's really important is when you're looking at these things is to look at the y-axis, because almost all of these plots are just scaled to whatever the maximum value is. So in this case, there's relatively small movements. The radians, which is the way rotations are measured. So if you remember back from high school math, there are 2 pi radians in 360 degrees. So, whatever. It's not the most user-friendly sort of way of doing it, but it does mean that this is a small amount of head movement. This was a good participant. But other software packages do it slightly different. So FSL, which is the Oxford version, chooses the middle volume of the run. So rather than use the beginning volume as the reference point and then have it shift and shift and shift over the whole time series, what FSL chooses is the middle point so that it can only be half a time series away. But these are the same data where the reference points are shown here with these two red arrows. And you can see that the pattern of the plots is exactly the same, but the size of the shifts are slightly different because of the change in the reference point. The key thing with estimating motion parameters is that you are always doing it relative to some reference. And there is no right or wrong reference, but you need to be aware of what's been chosen as the reference. In SPM, it's going to be the first volume after you've deleted the dummy volumes. Then what we need to do is to be able to figure out what the difference is between one volume and our reference volume. Okay, so if in this image, I have two very, very simple volumes shown in these gray 4x4 plots, and the X is going to be my reference volume, my Y is the volume I want to figure out, well, how different is Y from X? Well, the simplest way to do this is to use a sort of a sum squared error. So if I just simply, count the number of voxels and label it from top left to bottom right, then I can compare, well, how similar are these voxels? And the easiest way to do that is to say, well, what's the difference in the intensity between X1 and Y1, the voxels in the same position, and whatever that number is, square it, right? So if that number is 0, they're the same, then there's no error. If that number is positive, then there's some error. But if it's negative, then there's some error too. And the reason that we're squaring this is because we don't want the positive and the negative to add up to 0. That would suggest that there was no overall error when that's wrong. Whether it's positive or whether it's negative isn't important for us. It's just that they're not the same, and it doesn't make a difference what the direction of that error is. So as a result, we square these. And this is a simple error function that you've seen probably in statistics before. And what you can do is say, okay, well, then for any two images, I can compute the cost function, right? So I can get an error score. And what I want to do is make that error score as close to 0 as possible. Because if it was 0, it would mean the two images were perfectly aligned, and the difference between them would be nothing. You never really get it to 0 because, of course, there's other things that are going on in the image that have nothing to do with head motion. It's just that head motion is such a big effect that this will be the dominant source of error, and that's why we want to minimize it. I should point out, there are tons of other cost functions that we can use. And in fact, next week when we talk about normalization, we're going to talk about some of those other cost functions. But for today and for our purposes, this is perfectly fine. And they all do the same thing. They all give you a measure of how different two images are, and you want to minimize those differences. Okay, so with that in mind, you could imagine doing this in a sort of painfully computationally intensive kind of way, where you say, look, I have these two images, and they're right now, these are the images that I'm given, a reference and my volume. What if I change that volume by rotating it in X 10 degrees, 20 degrees, 30 degrees, or negative 10 degrees, right? In which case I could compute a cost function for each of those different images, and I could just see which one was the lowest cost. And that's what I'm sort of showing here. So 0 is where we start. If we were rotating in X, which if you recall is sort of left-right, so this is the sort of nodding motion, and you can see that with the two brains here shown 1 and 2, it's the same image. I've just simply rotated brain 2 in this nodding direction in a positive X. So what I need to do to correct it is to rotate it back. I need a negative X rotation. And if I do that, that's going to give me this global minimum, right? That'll give me the point that's optimum in this cost function. On the other hand, what I need to be careful of is that there are local minima as well, right? So if all I had done was said, okay, well, I'm going to try moving more positive rotations in X, well, I get to a point fairly quickly where things have gotten better, and then they start to get worse again. That's this first local minima. And I might sort of stop there and say, okay, well, I've clearly gotten to the point that's best. But the problem here is that this could be a very complicated little curve with many of these little local dips Whereas what I want to do is make sure that I find the largest effect, the global dip. That's the point where I'm going to suggest is the optimum cost minimization. And that is the point that I'm going to use for realignment. The algorithms to do that aren't super complicated, but they're way more involved than I want to get into here. This is, if you're really interested in these things, these are essentially machine learning problems. And I would encourage you, if you're interested in sort of the AI machine learning side of things, then to look at optimization. That's what these problems are. They're minimization or optimization problems. And SPM, FSL, all the software packages have the tools built into them, and they solve it for you. And I've only shown this in one of the 6 degrees of freedom, but you can imagine doing this for the other 2 rotations and the other 3 translations, so that you get 6 estimated motion parameters per volume that make the data as unmoving as possible. That's the realignment process. So this is the kind of plot that you get out. I've actually used an FSL plot here just because I think it's easier to see them all in one spot. But what you can see is you get estimated rotations in radians, which is not the most useful thing in the world, and then estimated translations in millimeters. Now, at least that's sensible. And the nice thing with this subject is if you just looked at the plots, it looked like maybe around volume 60, this person moved a lot. But if you look at the y-axis, you can see that the huge movement from volume 55 to volume 60 is about 0.2 millimeters, right? That is not a big movement. That's a really good subject. The problem is that all of these software packages scale these to the largest movement. If the largest movement is something that's under a millimeter, don't worry about it. Similarly, if you convert these radians to degrees and you discover that it's under, a degree or 2, not a problem. That's a good participant. But that does raise the question of how much data or how much movement is too much? Like, at what point do we say, that really is a problem, this person's been really difficult? And the heuristic that we use, because there is no correct answer, is that if the movement is larger than the minimum dimension of a voxel, then it's too much. So for instance, if you were collecting data that was 3 by 3 by 3 millimeter voxels, which is a fairly typical kind of fMRI study at this point, then if you have movement that's larger than 3 millimeters or 3 degrees, yeah, that's probably too much movement. The realignment process is going to introduce additional artifacts in trying to deal with this. Anything under that is much more likely to be okay and handled fine through the realignment process. Now, it is a heuristic. It's a rule of thumb. It's not a hard and fast rule. However, so the issue is, well, what if they were 2.9 millimeters? And you have to look at your data. I mean, it may be the case that that's still too much based on the way this person moved and it's introduced artifacts into your data. But what I would suggest is if it's more than the minimum voxel dimension, it is too much. And in that case, in all likelihood, you need to throw that data set out, which means that you have essentially noisy data from one participant. Just for reference, this isn't wildly different than doing a reaction time experiment where you have 60 participants and it was a very simple sort of word recognition task, and on average people respond between 500 and 1,000 milliseconds to these words, but you have one subject who's there at about 2.4 seconds. Well, look, those data are awful, right? That for whatever reason that person wasn't paying attention, they found the task exceptionally difficult, well outside the normal paradigm. Again, you just throw that data out because it's outside of the range of normal behavior. The same is true here. That much head movement, more than the minimum dimension of a voxel, is outside the range of normal head movement, and it's outside of what we can easily correct through realignment. And then I also want to point out this one exception to knowing the experimental paradigm. If you're doing a blocked paradigm, and you see that your motion actually seems to be in blocks, then that's something that's a little bit worrying. So if people are only moving their head in accordance with your experimental paradigm, then the variance that you're throwing out due to head motion is also very much related to the experimental variance that you've planned. And if that happens, these data are absolutely useless. There's nothing you can do, and of course you have to chuck them out. So if you have a block design and you see that you get motion effects like this, so that is to say a block of task comes on and people sort of focus and they pay attention, and meanwhile their head's going back, and then it's rest and then they focus. So they're doing this in a kind of consistent way that fits the paradigm. There's nothing recoverable in those data.